Greetings students, welcome to another lesson from iCampSA. This lesson will be on functions. We'll be covering characteristics of the different four functions that are done in grade 10, which is your linear function, quadratic function, hyperbola, and the exponential function. And then we'll also do some exercises on those functions. Without wasting any more time, let's get into it. So this installment will be just additional characteristics of the four functions. First thing first, let's cover the functional notation. You will see that in your exams or in your exercises, often you will find that the function is written as f of x is equal to some equation. So what you must know is that this f of x here, or f of x, represents the output value. It represents the output value, which is for the most part is y, because the variable that we use most of the time is your x and the y. So f of x stands for the y value. And another important thing to note is that the brackets that you see there on that notation of f of x do not mean or represent multiplication. So this doesn't mean that you should multiply f with whatever is inside the bracket, but instead it corresponds with the y value. So instead the y value corresponds with f of x, as I've already mentioned, that f of x corresponds with the y value, the output value. It's the output value of our equation of our function. So those brackets that you see there, they don't mean that multiplication must be done. And the way to read this notation is f of x is equal to x squared. For example, this is just an example, is equal to whatever is on your right hand side, or whatever is on the right hand side of the equation. So for instance, with that example that we made here, the way you're gonna read it is like f of x is equal to 3x, or 3 multiplied by x. And then for example with this one we are covering here, f of x is equal to 3x squared. Is equal to x squared, the one that I highlighted there. And another important thing with the functional notation is that other letters can be used instead of. It's not always going to be the function of x is equal to some output, but you can use other letters can be used, like your g at x, or g or h at x, p at x. So you can find that, maybe for example, you can find a situation whereby you are given g at x is equal to maybe x squared plus 1. So other letters can be used in this functional notation. So let's quickly do this example to try and drive this point that we were making home. So for example number 1, we are given that function, which is f of x is equal to x squared plus 4x plus 1. So as you can see with the x squared there, that this is a quadratic function. So we're asked to determine the value of the function, at 2 for number 1, the value of the function. So we are asked to we are asked to determine the value of this function f of x at 2, f of x at 2, because remember that what is inside the brackets is our x, or it's our input value. So we're asked to find the input value, we're asked to find the output value at that input value of 2. Okay, let me write this down. So we're gonna say for number one, whereby we're asked to determine the value of f at 2. So we know that our function is f at x is equal to x squared plus 4x plus 2. And then now we are asked to find the value of f at 2. So wherever we see x, we're going to substitute now what? We're going to substitute 2. so we're gonna have 2 squared plus 4 times 2 plus 1, and this is gonna be what? 2 squared is 4 plus 4 times 2, which is 8. So that is 12 plus 1. This is equal to 13. So f at 2 is equal to 13. So that is how you go about doing that. And then for number 2, we are now asked to find the value of f at negative 2. So f at negative 2, we simply substitute negative 2 wherever we see what now? Wherever we see x. So negative 2 squared plus 4 times negative 2 plus 1. This is gonna be equal to what? Negative 2 squared is 4 plus 4 times negative 2, which is negative 8. So it's minus 4 plus 1. This will be negative 3. This will be negative 3. And then for example number 3, please pay attention. Now example number 3, we're given f at x plus 3. F at x plus 3. So you see what happening now? That 3 is not the value of x that we are supposed to substitute wherever we see x, but now the 3 is added to the output. The 3 is added to the output. So the way we go about this one is we're gonna say, what is f at x? F at x is equal to x squared plus 4x plus 1. This is f at x, and then we're asked to add what? To add 3 on top of that. So that's what I was supposed to say, f at x plus 3. Okay, so this one would be equal to what? X squared plus 4x plus 1 plus 3. We add like terms, so it's gonna be plus 4. So f at x plus 3 is gonna be this thing, or it's gonna be this thing that we have here. It's gonna be this thing that we have here. Okay, let me actually remove this because it can be a cause of confusion. When this is not equal to this, it's mathematically correct, because when we transpose, that 3 is going to be negative on the other side. So I'll just leave it like this. But that is how you go about answering that question. So for number 4, we are to find f at x plus k. F at x plus k. So look at that k now. It is inside the bracket. So what do we do here? What do we do is that we're gonna wherever we see x now, we're gonna substitute x plus k. So this one is gonna be equal to x plus k squared plus 4. Where we see x, we substitute what is within the bracket. Plus x plus k plus 1, and then we can simplify this. This one is going to be x squared plus 2xk plus k squared plus 4x plus 4k plus 1. So this is the expanded version of what we had there on the previous step. Let me see, I wanted to see if we had like terms. So apparently we do not have like terms, so it is even better to just leave it like that one in the step number 1. And then for f at x, for number 5, we're asked to find f at x plus k minus f at x. So what we had there, but we're now gonna subtract f at x. So for number 5, we are to find f at x plus k minus f at x. So what is f at x plus k? F at x plus k is x squared plus 2xk plus k squared plus 4x plus 4k plus 1. And then we're gonna subtract f at x. What is f at x? F at x is x squared plus 4x, let me put this in bracket, plus 1, because the sign has to change. So when we subtract this, x squared will cancel the x squared, 4x will subtract the 4x, 1 and 1. Okay, that's right. What we are left with, we're gonna be left with 2xk plus k squared plus 4k. Now let's put it in the correct order. This is gonna be k squared plus 2xk plus k. Okay, so that is how you will go about answering that question, answering that question. Okay, let me see. Oh yeah, that is that with the functional notation. Let's go ahead and do a look at more characteristics of the function. So these ones are global. So in terms of they exist for all of the function we've considered. First thing first, we have the domain and range. You may have already come across, but what is a domain and range? So a domain, first thing first, is a set of all x values. The input values that are used for that function, for a particular function that we'll be dealing with. I usually say the way to look at it is it's like for a given function, which x values does our function exist as, and then we have to write that down, so there are some notations that we use in order to write to represent or to present a domain and the range. We'll cover them in shortly, but domain simply deals with the x values. It simply deals with the x values of the function. Okay, and then we have the range. The range is the set of all the y values. The outputs, that are obtained from the x values. So the range simply looks at all the y values for which our function exists at. Okay, so that is the range. And then we have different notations that we use in order to represent the range or the function. So first thing first, we have a list notation, which is x is the for example, x is the element of, and then we're gonna list all the values. That we, let's say if we are considering the domain, we're gonna list all the x values for which our function existed, and this typically works when we are dealing with this one. Typically works when we're dealing with discrete function or non-continuous functions. That is when we can list the notation, or we can list the we can use, why do I keep on saying list? We can use the list notation, but for the most part in grade 10 you're gonna be using the interval notation, because we deal with continuous functions, so this one would be the one which is commonly used. And then a few things that you have to know about the interval notation. We use parentheses and brackets. So these two, they represent the different things, but yeah, we use the parentheses and the brackets. So the parentheses we use to show that whatever value that we have put there, it can be either maybe negative infinity or it can be 0, but it means that value is not included in our function. It's not actually part of our function. So you'll see, especially when we deal with the range for hyperbolic function, where some values, as we know that we have an asymptote, so it's gonna be both for the hyperbolic function and exponential function, where we're gonna use the parentheses a lot, because there are some values for which those functions, they don't exist. We have that asymptote level where the function will approach but it will never touch. And then next we have the square brackets. The square bracket, it means those values that we are using to represent our domain and range are included. It means included. So the square bracket, they simply represent inclusivity. And then next we have this union symbol. It's just the u, a small u. So the union symbol is used to connect separate intervals, so once again, when we are dealing with hyperbolic function, whereby there is a break in our function, there is some value where our function doesn't exist. So we have to use the union symbol in order to represent our domain and range. Let's go ahead and do this example so that you guys can understand what we are talking about. Remember, domain deals with what? The domain deals with x values, and the range deal with y values. Okay, so we have example number 2. State the domain and range of the following functions. We have asked to state the domain and the range of the following functions. So the first one is a discrete function or a non-continuous function, and I said for a non-continuous function, that is where we're gonna use what? The least notation. So the domain, and remember that for the domain we are only considering the x values. So we're just given coordinates for this one, so we're gonna say the domain, okay, x is the element of, and then we use braces, the least notation. Our function starts at -2, -1, 0, and 1. So braces, that's the least notation. And then let's go ahead and do our range. For the range, we are looking at the y values. We are looking at the y values. These are the values that we are looking at now for the range. So we say y is the element of, we put our braces there, the braces. So y is the element of, we start at -2, -1, 1, and 2. 1 and 2. So that is the domain and range for the first function. Next, for function number 2, we are dealing with something, so this is actually it is a continuous function, but it starts from -2 and 2 and ends at 2 and 2. I want you to just pay attention to those bubbles that we use there at the ends of this function. One is shaded, and a shaded button, it means that value is also included. So if the value is included, what do we use? We use square brackets. And then if the bubble is not shaded, it means that value is not included. So let's go ahead and do the domain for this one. So the domain, we are looking at the x values, so it's gonna be the same. I didn't notice, I should have used different coordinates when making this example. But anyway, the domain, our function starts from -2 up until what? Up until 2. So x is the element, remember, it's included, square bracket, -2, all the values from -2 up until was up until 2, round bracket, because the 2 there on that second point is not included. Okay, and then let's go ahead and do the range, looking at the y values. And then the y values, this function goes from let me do something different. In fact, hopefully this will help. Let's change that coordinate to 3. And this one to -3, so that you can see what we are looking at. So what are the y values for which our function exists? We have y is the element of square brackets, that -3 is included all the way up to 3. That is our range. Hopefully that makes sense. Okay, and then here we are now. These are continuous functions. The domain and range. So for this function, domain and range, if the function has arrows like this, it means that the function goes continuously. It will continue to infinity in this direction and also in this direction, as it will also continuing infinitely to the y values. So the domain for this one, it's x is the element of from -infinity. And another important thing when dealing with the domain and range is that we always start with the small value and ends with the big value. So we go from -infinity to +infinity because the function exists for all the x values. Okay, and then let's deal with the range now. let's deal with the range. So range y values, y is the element, once again negative infinity to positive infinity. Okay, next let's do number 4. Number 4, it's a parabola, and look at this. Our function, it goes from this direction to this direction, and another important thing to remember, that with the parabola, as it is going upwards, it is also expanding in this direction, so just don't look at the function like this, that maybe if we have a value here, then the function ends at 3. No, the function is continuous. It is still moving in that direction, so that is what is represented by the arrows there. So for a domain of this function, we're gonna say x is the element. As we can see that the function exists for all the x values. X is the element of negative infinity to positive infinity, and then the range, pay attention now. The range, as we can see that the function only exists from the origin going upwards for the y values. We don't see the function anywhere below the x-axis, so it means that the function doesn't exist below there. So our function exists from the origin at that point 0 going into positive infinity. So our range is going to be y is the element of, remember 0 is included, the origin, from 0 to positive infinity. That is our range. Okay, and then next we have number 5 and number 6. This one, number 6. Okay, so the range for this function, we are dealing with the hyperbola. Sorry, the domain for this function, we're dealing with the hyperbola. The domain, look at the function, it goes all the way, and then there at 0 the function does not exist. It doesn't touch the level of 0 where x is equal to 0, and then we jump, the function will start existing, and then continue all the way up to positive infinity. So the way that we're gonna represent this domain, we're gonna say x is the element of negative infinity, it's not included, round brackets, all the way up to 0, round brackets, but the function jumps. It is also available on this side. That is where we use now the union symbol, and say, and the function goes from 0 to positive infinity. That would be the domain of this function. That will be the domain of this function. Or I want to write another way that you can do this, or you can say x is the element of all values. In fact, x values from negative infinity to positive infinity, and you can say x, but x cannot be equal to 0. That is another method if you have forgotten to use the union symbol. Okay, then let's do the range. So the range of the function, we go from this is negative 2 to positive infinity, and we start from negative infinity all the way up to negative 2, and then it jumps. So we're gonna see it's y is the element of negative infinity. Always starts with the smaller value, negative infinity to what? To negative 2, round bracket. Negative 2 is not part of this function. Union negative 2, round bracket, to positive infinity. Okay, there we have that. that. Okay, and then next let's do the domain for that function number 6. Function number 6, we can see that, okay, this is a hyperbola, and then the asymptote is x is equal to 0 and y is equal to 0, so those ones are not included. So we're gonna see for the domain, x is the element from negative infinity to positive infinity, but x is not equal to 0. X is not equal to 0. In fact, you can even put that but x is not equal to 0. And then for the domain, for the range, once again, y is the element from negative infinity to positive infinity, but y can never equal to 0. So that is how we deal with the domain and the range. Okay, so next, another characteristic that I want us to cover is increasing and decreasing functions. So what do we mean when we are saying functions are increasing and decreasing? So as you can see here, it is represented with those arrows, but in simple term, a function is increasing if, as the values, remember that when we are moving from left to right, the values of x are increasing. So if, as we increase the values, or yes, as we increase the values, or as the x values are increasing, also the y values are increasing. If that is the case, then we say the function is increasing. So that is what is meant by that. So that's how we see, in other words, an increasing function. So y values increases as the x values increases. And then on the other hand, if we move from left to right, the x values are increasing, but now the y values are going down like that. They are decreasing. That when we are saying now a function is decreasing. So y values decreases as the x values decreases. So if maybe we had a straight line function like this one, so with the straight line function like the one that you see there, as we are moving from left to right, remember the x values are increasing and the y values are also increasing for this function. The y values are increasing. For instance, we're gonna have let's say maybe a -2 and a -2, and then here we have, let's say, a 1 and a 3, a1 and a 3. So as you can see, that since we have moved from -2 to 1, x values are increased, but also for the y values we have moved from -2 to 3. So y values are also increasing. So that straight line function will be considered an increasing function. So that is how we see that is how we see an increasing function. Okay, and then next, just a reminder of the linear function and the formulas that we use when dealing with the linear function. We have that basic formula, which is y is equal to mx plus c. So the way that we have represented it, excuse me, I remember when we covered the linear function, I think it's y is equal to ax plus q, if I'm not mistaken. So it's basically the same thing. But as you move forward, you go to grade 11, grade 12, you'll see that generally the form that they use is y is equal to mx plus c, and that m there stands for the gradient. And the way that we calculate the gradient of a linear function, m is equal to, we take the difference of the height over the line. So it's y2 minus y1 over x2 minus x1. That is how we calculate the gradient. It's the difference of the height over the difference of the run. Okay, yeah, hopefully I didn't make any mistake there. And then another formula that you will see going forward is this one of this form, which is ax plus by is equal to c. So most normally what you're gonna do with this form, you'll have to rearrange it and make and make y to be the subject and make y to be the subject of this formula, and then whatever value that we're gonna find as the coefficient of x, whatever value that you're gonna find as the coefficient of x, that is gonna be your what? That is gonna be your gradient, so always the coefficient of x is our gradient. So let's say we rearrange this one, we're gonna have y is equal to c, or maybe let me just say negative a x over y plus c over over p over c over p. Yeah, so that negative a over p will be your gradient. Maybe let me rewrite this one as a over p x. Yeah, so this one here, that negative a over p will be your gradient for this case, after we rearranged after you've rearranged this formula or this equation. Okay, so and then next we have what? Quadratic function. So quadratic function has other characteristics that we didn't touch on. We have the maximum value. The maximum value is basically the largest value on the graph. It's the largest value on the graph, and this maximum value or the minimum value is generally your turning point on the function. So a minimum value is the smallest y value on the graph. So this graph that is facing up here, that point there, this point here, this is the smallest y value for this function which is facing up. So this one will be considered your minimum value, so this graph has a minimum value, but it doesn't have a maximum because it goes up infinitely. It goes up infinitely. So if this function was facing down, therefore we're going to have what? A maximum value. So the maximum value is the largest y value on what? On the graph. And then we have the turning point. So a turning point is simply the point where the graph changes from decreasing to increasing, or from increasing to decreasing. So for this graph, also that minimum value, there's, I've told you that most of the time the minimum value and the maximum value of a function will be your turning point. So that point here where our graph changes from going from decreasing to increasing is called a what? Is called a turning point. That is your turning point. That is your turning point. So, and then for sometimes it is also called a stationary point, because the trident is not changing there, it's just flat, so at exactly that point where the graph changes from decreasing to increasing is our turning point. So the turning point can also be a maximum value if the function was facing down like that, so that is that, and that is the turning point. And then next we have the axis of symmetry. So axis of symmetry is just a vertical line that divides the parabola into two congruent halves. So for this function, the axis of symmetry will be those y, the y-axis, basically the y-axis. That will be the axis of symmetry. So because once you have that vertical line there, this half of the function is almost like, or not almost, it's actually a mirror half of this function. So this one is your axis of symmetry, and as we have said that the axis of symmetry is a vertical line that divides the parabola into two congruent halves. Another important thing to know about the axis of symmetry for a parabola is that the axis of symmetry will pass exactly at the turning point of the parabola. So exactly at the turning point of the parabola. That's another thing. And then here are a few equations of the parabola. We have this standard point here. We have this standard point. And another thing that I think I forgot to mention that I did not mention when we're dealing with the parabolas is that the value of q, we know that it represents the vertical shift, but for a parabola, and when we are dealing with that form of equation, the value of q also represents the y value of the turning point coordinates, so for this parabola that we deal with in grade 10, the coordinates of the turning point, let me just do it like this. Coordinates of the turning points will always gonna be coordinates of turning point are gonna be 0 and q and some value of q, so that's always gonna be, because this function that has the axis of symmetry at x is equal to 0. So that's another important thing. And then another forms of the equation of the parabola as we're going to deal with as we go forward is the x-intercepts form, that we have here, or intercepts form. And what is special about this one is that it gives us directly the values of the x-intercepts, so we can directly read from the equation the x-intercepts. And then we have another form which is called the turning point form, and this one, it gives us the value of the turning point, the coordinates of the turning point. The h and the k are actually the coordinates of the turning point on that equation, but you're going to deal with these ones when you go to grade 11 and grade 12. For now, we're just going to be focusing on the first one, the standard form, the standard form. Okay, and then next we have the hyperbolic function. So a hyperbolic function, another interesting thing about them is that it has two axes of symmetry, so for the hyperbolic function, unlike the parabola which has the axis of symmetry at 0, the hyperbola has axes of symmetry that are actually diagonal, and then if it has not been shifted, the axis of symmetry passes through the origin, but once it has been shifted, the axis of symmetry will pass at the point of the asymptotes, or where the asymptotes meet, Okay, so yeah, for most of the functions we deal with in grade 10, they're only shifted vertically, so yeah, it will just pass there. The axis of symmetry, they move with the asymptotes, and then the equations for the axis of symmetry, if it has not been shifted, it's just gonna be y is equal to negative x, as you see there, and that negative x is because we have a negative gradient for that straight line, and then we have y is equal to x. But once this has been shifted, we also have to account for the shift that has happened, and then we know that the shift is represented by the value of q. So the new equation for the axis of symmetry with the decreasing axis of symmetry is going to be y is equal to x negative x plus q, and then the other one which has add the q, so it's y is equal to x plus q. And then remember that the standard equation for the hyperbola is y is equal to a over x plus q. If you remember that the a it represents the vertical stretch of the function, it represents the vertical stretch of the function, or how far is the function stretched from the x-axis, and yeah, just represent that. And also the shape of the branches, the shape of the branches, but I think just saying it represents the vertical stretch also accounts for the shape, because the more the function is stretched, also the shape would become wider and wider. Okay, and then next we have the exponential function. We have already covered the exponential function. It's y is equal to a multiplied by b to the exponent x plus q. So this is the general form of the exponential function, and the way that we see that we are dealing with the exponential function is that the variable x is n exponents. Maybe that one is worth noting. Variable x is an exponent, and hence why we call this function an exponential function. And then let's do some set of exercises, to sort of close this topic that we have been covering. Yeah, we'll just do this types of exercises, and then more videos are gonna follow, but we'll be just focusing on even much more exercises, in fact, and even some past papers, or even more past papers, if I may say, just more past papers. Okay, so this is exercise number one. Exercise number one. You are given, hopefully that is visible enough. We are given the following. Given f at x is equal to x squared minus 1, x squared. That should already tell you that we are dealing with what? With a parabola, and g at x minus 1 and g. So given those two functions, we are asked for number one to sketch the graph of f and g on the same set of axes. So generally, you know that what we do is just we take maybe some three values. We take some three values and do what's actually 3x inputs values to find the what you call this thing, to find the corresponding y values. But the easiest way to actually sketch a parabola, the easiest way is just to find the turning point and then find the x-intercept. That will actually give you 3 points that you can use to sketch your function. So in fact, I think it's worth understanding understanding how to do that, because when you move forward, you won't be inputting 3 random values in order to sketch a function. So you must know how to find the turning point from the equation, and also find the x-intercept. So for the turning point, we know that when we are given that standard form, the turning point will be TP is 0 and the value of q, the value of q. So for that function that we have there, which is f at x is equal to x squared minus 1, the value of q is what? Is minus 1. So therefore the TP is 0. The TP is, let me write going this direction. The TP is 0 and negative 1. That's the turning point. And then next, find the x-intercept. So find the x-intercept. Let y is equal to 0, because that is where our function will actually cut. The x-intercepts, if we do have them, because some functions they actually don't have x-intercept. But for this one, let's find the x-intercept. We say let y equal to 0. So f at x, remember that it's actually our y. So f at x is equal to x squared minus 1. I'm gonna say 0 is equal to x squared minus 1, and then we take the 1 to the other side. We're gonna have 1 is equal to x squared. We're gonna have to introduce a square root. So the square root is either positive and negative. Negative plus or minus the square root. What did I do? This is x squared. We are introducing the square root. I don't know why I'm writing there. So the square root is plus minus roots of 1. Therefore, we're going to have two roots for this equation, which is x is equal to 1 or x is equal to negative 1. Okay, so you could have found the same thing by maybe taking negative 1, 0, and 1, finding those three corresponding y values to sketch. But already here we have three coordinates. We have that first one of the turning point, very important, and then we now have these two coordinates that we have here, which is it's 1 and 0 and 1 and negative 1 and 0. Okay, and then next for the grx function, which is grx is equal to, we are dealing with this now. Grx is equal to negative 1. It's a straight line. We just need 2 points in order to sketch a straight line. We just need 2 points, so we can use 0 and 1. So g at 0 is equal to 0 minus 1. So g at 0, the y value there is what? Is negative 1. Negative 1. So we have 0 and negative 1. That's the first coordinate. We can call it coordinate A. And then let's find another point. Let's find g at 1. So g at 1 will be 1 minus 1, of which would be 0. So g at 1 for P is 1 and 0. 1 and 0. So we have 2 points. Okay. Once we are here, we can essentially sketch our function for this parabola or quadratic. We have 3 points, and then for this, we only need 2 points to sketch a straight line function. Okay, let's go ahead and do that now. Let's go ahead and sketch our function. Our functions. So calibrate the x and y axes. X and y axis. Another thing, remember that the coefficient of x squared for the parabola, which is a, it also tells us the direction of the opening. So if a is positive, that means our function is facing up. If a is negative, it means our function is facing down. Just wanted you to also remind yourself of that. Okay, so okay, this would be 1 2 3 4 5 5 6 5 negative 1 negative 2 negative 3 1 2 3 4 negative 1 negative 2 negative 3. Yes. Okay, let's start by sketching the parabola. We have first point there at 0 and negative 1, and then we have negative 1 and 0 here, and 1 and 0 and 1 and 0, and then we can sketch the function. It's gonna be of this nature. We shift it down a bit. That's our parabola right there. This is the function of f. We can label it. That's a function of f. Okay, and then we had the straight line function, which passes through 0 and negative 1. So it passes through here, 0 and negative 1. It also passes at 1 and 0 and negative, sorry, well, it's y that is 0, and y 1 and 0. Yeah, this is the point. That is our straight line function, which is the function of g. This one is the function of f, and the straight line is the function of g. Okay, and then next we are asked to determine the domain and range of f. F is the parabola. Let me add the page. Add page. Create. Let me add the page. This is for number 2. We are asked to find the domain and range of the f function, so of the parabola. So the domain for the parabola, remember that for the domain we are looking at the x-axis. So the function exists for all the x-axis. Therefore, we're gonna say the domain is x is the element from negative infinity to positive infinity, and then the range, let's come here, look at the turning point now. The turning point from negative 1 going down, we don't see the function, we don't see any branches below negative 1. So if we were to put maybe just a straight line there, or your ruler, anything below that 0 line, our function, that red line, our function doesn't exist. So the function only exists from negative 1 going upwards. So we're gonna say what the range, y is the element of, from what, square brackets, also negative 1 is included, negative 1 to positive infinity. That is your number 2. Okay, for number 3, if h at x is equal to f at x plus 3, write the coordinates of the turning point of h. Okay, so what do we have to do? We have to add 3 first on that function that we have there and see what do we get as the coordinates of the turning point. Okay, so for number 3, we are told that h at x is equal to f at x plus 3. What is f at x? What is that function? So h at x, we write it as it is. F at x is equal to x squared plus 1. F at x is equal to x squared plus 1. I can put it in bracket plus 3. Therefore h at x is equal to x squared. 1 plus 3 is gonna be, sorry, is it plus 1 or negative 1? It's negative 1. I remember that, man. We had a negative turning point, so it's negative 1. I made a mistake, sorry there. So it's gonna be it's gonna be x squared minus 1 plus 3. What is minus 1 plus 3? Is gonna be positive 2. Therefore, we're gonna have x squared plus 2. X squared plus 2. And that is the equation for the new function. That is the equation for the new function. And then we are asked to write down the coordinates of the turning point. So the coordinates of the turning point, I said we take the value of q and 0. So the turning point would be 0 and 2. 0 and 2. Okay, determine the maximum value of p if p is equal to negative h at x. Negative h at x. So now and the reason why we have a maximum value, or yes, the reason why we have a maximum value now is that this function p will be a negative version of the function of h. So it's going to be facing down. The turning point is there. It's going to be, yes, it's going to be reflected and it's going to be facing down. Okay, so let's start by writing the new formula that we're going to have for p at x, and then we'll determine the maximum value, of which essentially will be the turning point, but we're just going to write the value, not as coordinates. So p at x is equal to negative h at x, so therefore p at x is equal to negative, what do we have for h at x is x squared plus 2. Let's multiply out by that negative. Therefore we're going to have negative x squared minus 2. Negative x squared minus 2. That's the new equation for the what is this thing, for the function of p at x. Therefore now the maximum value, which is the turning point, will be, the maximum value will be y is equal to negative 2. Y is equal to negative 2, because the function is now reflected about the x-axis. That is what that negative does to the function. Okay, so it's just going to be that value of the turning point. This is the maximum value, So if our function was facing up, this one is going to be positive first thing first, and then this one was going to be the minimum value, not the maximum value. Okay, sketch the graph of h and p on the same set of axes. Sketch the graph of h and p on the same set of axes. Okay, for the graph of h, this is going to be number 5. So we have the graph of h and p, these two graphs. Okay, let's calibrate. Okay, we have we have 1 2 3 4, 1 2 3, negative 1, negative 2, negative 3, negative 1, negative 2, negative 3. Okay, let's start with the graph of h. The graph of h is that equation. First thing first, the coefficient of x is positive, so this graph is facing up, and the turning point is what is 0 and 2. So the graph would be having a turning point here, and it is facing up. Therefore it doesn't have the x-intercepts. Therefore this graph will look something like this. Okay, will look like this. That is the graph of h. Okay, and then the one for p, the graph of p, the coefficient of x is negative. That is your a. Coefficient of x squared is negative. Therefore this graph is facing down, and the turning point is at -2. That's the maximum value. So here we'll have a turning point. Therefore this graph will look, why do I go so wide? So that is how the graph of h is gonna look like. That is how the graph of p, as you can see that the graph of p is just the graph of h reflected about the x-axis, Let me extend this one, about the x-axis. Okay, and then for number 6, determine the y-intercept of the graph of y is equal to -g at x. The y-intercept of the graph, okay, not the graph that we have sketched here of g, but -g at x. So we have to find the graph of y which is -g at x first. So let me add another page. Custom, add another page, create. This is number 6. We are asked to find the y-intercepts of the graph of what? Of the graph of y is equal to negative g at x. We are also find the y-intercept. Find y-intercept. Okay, so first thing first, we have to find the graph of y with the -g at x. So the graph of g, first thing first, is x minus 1. Therefore the graph will be negative x minus 1 multiplied by the negative. It's going to be -x plus 1. So, and then once we are here, we can find the y-intercept. So for y-intercept, let x equal to 0. Okay, then we go to our graph now. Y is equal to -0 plus 1. -0 plus 1. Therefore the y-intercept is equal to 1. Y is equal to 1. That's the y-intercept. And then next we have number 7. Determine the x-intercept of the graph of y is equal to g at x plus 2. So first thing first, we have to find the graph of y, which is g at x plus 2. Y is equal to g at x plus 2. So we have for number 7, and then we find the x-intercept, remember. So for number 7, we have to find the x-intercept for the graph of g at x plus 2, and we are asked to find the x-intercept. Let me double check that. Yes, the x-intercept of this graph. So first thing first, let's find the graph of y, which is g at x plus 2. The graph of g at x is x minus 1. So we have to go to the graph of g at x. The graph of g at x is equal to x minus 1, if I'm not mistaken. Yes, it's x minus 1. And where we see x, because now that x minus 2 is within the bracket, that x minus 2 is within the bracket. So where we see x, that is where we have to substitute that x minus 2 now. X plus 2, my bad. So g at x plus 2 is equal to x plus 2 minus 1. Therefore this will be equal to x plus 2 minus 1 will be x plus 1. So this is the graph of g of y now that we have, is y is equal to x plus 1. Okay, and then we can find the x-intercepts. So for for x intercept, let y equal to 0. Therefore we're gonna have 0 is equal to x plus 1. We take the 1 to the other side, therefore x is equal to negative 1. That is where our graph will cut the x-axis at x is equal to -1. At x is equal to -1. Okay, so that is that for today's lesson. Or we're gonna have another lesson tomorrow. Another video shall be shipped, and then we'll be doing more exercises like this, where we're just answering questions concerning the functions that we have dealt with. I hope you learned something from this video, and until we meet again, I wish you good luck and good studying.